10 to the power minus 3 kilograms per mole. So once applying that particular value here, we can calculate the value for thorium also. That was point is 8.372093.023 10 to the power 40 Kelvin. So that's the Thermos point for thorium. But we have a problem. At these high temperatures, will the atoms or will the molecules behave as atoms or molecules? As we assume, the atoms and molecules will be disintegrated at these high temperatures. So after disintegration, there will be only subatomic particles. So now we are going to calculate another Laplace point for subatomic particle. The smallest subatomic particle that we can use to calculate a temperature is the electron. So electron, Laplace point for electron. So the molar mass for electron is 1 divided by 1840 multiplied by 10 to the power minus 3 kilograms per mole. Kilograms per mole. Kilograms per mole. So once we are applying this particular value into here in this place, what will happen? The value will come, the Laplace point for electron will come as 1.961168886 multiplied by 10 to the power 9 Kelvin. But is it possible in the real universe? As we think, yes, it is possible, because in metallic bond structures we know that the electrons are actively behaving, actively vibrating as particles that carries thermal energy. So electrons are vibrating to carry thermal energy. So electrons are actively participating in creating thermal energy. So we can assume that this particular value is one of the most possible temperatures for the highest temperature that can be existed in the universe. 1.961168886 multiplied by 10 to the power 9 Kelvin. But there's a problem as well. Electron can never achieve the speed of light. Electron is a particle with a mass and can never achieve the speed of light. So the actual temperature that we can obtain is going to be a little less than that. But how to calculate that one thing? In the cathode ray tube experiments, we have seen that the electron can achieve the speed of 0.8 of the speed of light. So in the cathode ray tube experiments, we have seen that the electron can achieve 0.8 of the speed of light. So we can assume that if the electron is vibrating to create a temperature, then it can vibrate at a maximum speed of 0.8 of speed of light. Now we are going to calculate another temperature for this particular movement as well, and let's move on from that. Okay, so now we are going to calculate those temperatures as well. As I mentioned earlier, the speed of light is still not possible for the electron to keep as the fastest moving speed of it. But in the cathode ray tube experiment, we have seen that the electron can achieve 0.8 of the speed of light. So now we are going to consider that the electron is moving at the highest temperature. At the highest temperature, electron is moving at 0.8 of the speed of light. Now we can apply that particular speed to the equation again. F is the molar mass of electron, C bar square. For C bar square, we can apply now 0.8 multiplied by the speed of light and square. So this is the molar mass of the electron. 1 divided by 1840 multiplied by 10 to the power minus 3 kilograms per mole. And multiplied by C bar square is now 0.8 of the speed of light and square. Divided by 3 is 3, R is 8.314. So finally, from this calculation, we can take a value of 4.1836190397 multiplied by 10 to the power 8 Kelvin. So this is the temperature. 4.1836190397 multiplied by 10 to the power 8 Kelvin. But is this possible as well? Yes, as we think, yes, this is possible, but still we have a small doubt. Can an electron alone behave as particle which creates a temperature? For that, we got another solution. So now we are keep taking the linear momentum conservation for the removal of electron from a thorium. So as electron jumps out from the thorium atom is repulsing away. So at high temperatures, even thorium atom is it's a heavy atom, but at high temperatures, even thorium atom can behave as a gas. So now we are considering that electron is jumping away, and the electron jumping away with the speed of 0.8 of speed of light, and thorium atom is repulsing. The repulsing speed is the highest speed of thorium atom that it can achieve, and from that particular speed, thorium atom is vibrating by keeping the highest temperature of vibration, and from that particular vibration, a temperature is getting generated. Now let's calculate what is that particular temperature. So again, for the linear momentum conservation, we can do like this. So here, the electron moves this way with 0.8 of speed of light. The electron, so the speed of electron, 0.8 of the speed of light multiplied by the mass of electron is equal to the repulsing speed of thorium multiplied by the mass of thorium atom. So we can consider the relative masses only because other units are getting cancelled out. So we can say that the velocity of thorium atom V1 is equal to 0.8 multiplied by 1 divided by 332 multiplied by 1840 ms minus 1. So finally the value will come as 532 ms minus 1 is the highest velocity that a thorium atom can achieve. Then from that velocity, thorium atom is vibrating now. Let's calculate what is the temperature going to be. T thorium real, that cross point of thorium real, is equal to m square bar divided by 3r. M is for thorium 232 multiplied by 10 to the power 232 multiplied by 10 to the power minus 3 kilograms per mole. The speed is 532 is square divided by 3 multiplied by the universal gas constant 8.314 Kelvin. Finally, the calculation will come like this: 2,800,052.12 Kelvin. So this is the temperature, the real temperature of thorium that it can achieve. So for now, these two temperatures can be considered as the highest temperatures that we can observe in the universe. So today the video ends from here, and thank you for watching. And also I have a huge request for all of you. If you have different calculations, if you have different suggestions, please upload them in the internet or anywhere, and please provide us a link also. And also you can put in comments what are your values, what are your calculations. We are going to consider all of them when we are upgrading our experience about these experiments. And let's see another day with another video. Let's meet in another day with another scientific video, same like this. Until then, wish you all the best for all your activities in academic careers. Thank you very much.